Welcome guys, how you doing? Today is the fifth session of chapter 3 of Fluid Mechanics 1, and the title is Static, Stagnation, Dynamic and Total Pressure. So follow me with the whole video. So, as I told you, today's subject is static, stagnation, dynamic, and total pressure, which is from section 3.5 of chapter 3 of Fluid Mechanics 1. Before going on instruction, I'm willing to introduce myself. My name is Amir Raza Talaqat, and my email address is amirrazatalaqat@gmail.com. Please don't hesitate to note your emails to me, or you can just provide your questions in the comment side of this video. I try my best to give you the answer as soon as possible. So, the concept which is associated with the Bernoulli equation is dealing with stagnation as well as the dynamic pressures, which means along a streamline, as we are moving from this section to this part, pressure rises. The pressure rise is burdened with the changes in kinetic energy until it reaches to the rest. Each term of Bernoulli equation, as you know from the previous session, is termed as the pressure, which is force per unit area. They could be described as PSI or Newton per square meter. The first term P in Bernoulli equation is regarded as thermodynamic pressure and also the static pressure. As I told you, we can calculate it from the thermodynamic relations. However, there is another method to give the values to the static pressure, which is during a hole in a flat surface and fasten a piezometer tube. As you see in here, we have a plate full of water that is dropped into the plate. For calculating the pressure at point 1, which is hydrostatic pressure, as we have a gamma term as well as the height term, we can calculate it from P3 plus gamma H31. The P3 itself is calculated from point 4, which is gamma H43. So we have the total P1 as gamma multiplied by H43 plus H31, which is totally the H, because as I told you, we are considering it as hydrostatic pressure. As we are moving down, the pressure increases. It's based on the concepts that I taught to you in the chapter 2. So moving along this line from point 1 to the point 2, there's a piezometer here. At the inlet, there's a tip. When a streamline hits the tip, there's a stagnation point, which means the velocity reaches to its minimum, which is 0, and the pressure goes to the climax. When it goes up to the height h, we can have the p here as P1 plus 1 over 2 rho V1 to power 2, which is regarded as dynamic pressure. These are the demonstrations that I gave to you in previous seconds. So the stagnation point in here is the highest pressure happening in the streamline, because it's the combination of the static pressure happening at P1, which used to be the hydrostatic one, plus 1 over rho V1 to power 2. So another fact is that when we are considering a streamline, when it reaches to an object, two situations might be happening. First of all, the stagnation point might be happening on the top, and the second to that might be happening in the bottom side. It depends on our consideration as well as the geometry. So as you've seen here for the baseball, the stagnation point is happening at the front side as long as the streamline is heading to the front. As long as it's symmetry, there is no matter how we consider the stagnation point. The circular baseball is a symmetric, so as it's confronting the streamline at the front side, we can regard the stagnation point happening in the front side. You all have gone to the car wash. They are using the water jets. The water jets are used to remove the dirts. When the water jet hits the body of the car, the stagnation happens on the body of the cars, where there's a maximum pressure. As you see in equation 3.15, every term of Bernoulli equation are pressure terms. If we neglect the elevation, the maximum pressure happening is going to be the stagnation pressure. So hydrostatic pressure, dynamic pressure, static pressure, dynamic pressure, as well as the hydrostatic pressure are going to be combined together to reach the total pressure, which is constant along the streamline based on the Bernoulli equations. One of the most appropriate methods that we can derive the equations between between 2 points in a flow line is the knowledge of P2 static, which is based on the values of static as well as the stagnation pressures calculated from the fluid speed. As you see in this picture, we have the P dot here. The P dot is the object which is connected to the sides of a pipe, and it can be consisted of a pressure gauge above it to calculate the pressure. As you see in this part, at point 2, the stagnation pressure is happening. Since the streamline is going ahead to the point 2, we have the term of 1 over rho v1 to power 2. When it reaches to the point 1, it's going to be relatively calculated as static pressure. If we have it in a horizontal line, let me just write it here. If we consider this as a horizontal line, we can, it means that we have the pressure P1, point 1 in here, and the point 3 in here. So when the flow is going on a streamline between point 1 and point 3, at point 3 we can have the calculations of the pressure like P plus 1 over 2 rho V1 to power 2. It's going to be the same for the point 4 as well. So the velocity is calculated as a square root of 2 multiplied by P3 minus P4 totally divided by density, which is equation 3.16. In this figure, we're going to see the structure of the pitot tube, which in here we have to calculate the stagnation point, and the holes in this side are calculating the static pressure. Once again, this is the entrance of the pitot tube. Going inside, we have one other stagnation pressure happening in this side. This concept is really applicable for the pilots who are calculating the airspeed. So in this example, I'm going to solve to you the pitot static tube, which is example 3.6. I'm going to demonstrate it in a written text. So follow me with it. So welcome guys to this part, which is problem solving of, let me just focus that. Yeah. It's the problem solving of example 3.6, which is about pitot static tube in chapter 3 of section 3.5. The question is, we have an airplane flying at velocity of 200 mile per hour at an elevation of 10,000 feet. In a standard atmosphere. It wants us to determine the pressure at point 1 far ahead of the airplane, the pressure at the stagnation point on the nose of the airplane point 2, and the pressure difference indicated by a pitot static prop attached to the fuselage. So, based on the information that we can take from table C.1, the static pressure at the altitude of 10,000 feet is P1 as 1,456 pound per square feet, which is absolute and is about 10.11 psi gauges. And also the density is 0.00 1,756 slugs per cubic feet. As we are studying the steady, let me just bring the green one. We are having steady, inviscid, incompressible, as well as at an elevation without elevation changes constant. We can use equation 3.30. That is, P2 is equal to P1 plus 1 over 2 rho V2 square, power square. We have this as 200 miles per hour, which is 293 feet per second. And as we reach to the stagnation point 2, V2 is 0, as I told you in the instruction. Then we can replace all of the things. P1 is 1,456. Rho is 0.00 1,756 slugs per square feet, and also a pound per square feet, and it's cubic feet. I made a mistake, sorry guys. Divided by 2, then we can have the P2 as 1,456 plus 75.4 pound per square feet. The difference in here is the 75.4, which is the gauge. which is the pressure of the gauge, P2 as gauge, which is rho V to power 2 over 2, which is P2 minus P1. So the difference is also going to be 775.4, which is 0.524 psis. Welcome back, guys. As you have already known, it's not an expensive way to identify the fluid speed based on the pitot tube. However, we must be aware of static as well as the stagnation pressure, which are calculated from the fluid speed. It means a high rate of accuracy is needed to design the pitot tube or to buy it. As long as the whole kinetic energy is going to be converted to the pressure rise, it is required that we have the pitot tube as the smooth holes as well as no berries or no imperfections. As you see in figure 3.8, when we have the tip either in this part or this part, the pressure rise might be having the variations. The best situation is happening in this figure, which there are no imperfections, and the P1 is equal to total pressure. This is the graph in which the pressure variation is shown. When the streamline is going to the tip of the pitot, it's gonna increase exponentially. When it reaches to the point 2, it hits the climax. Moving forward, reaching to point 1, it's gonna be converted to the static, and once again when it reaches to the principal to the tube itself, once again the stagnation pressure rises exponentially. In order to have the pressure taps properly, one of the methods that is suggested to calculate the static pressure is to have the pitot static tube as designed as this, to be designed as this. In this picture, as you see, there are 3 pitots in 3 different locations. When the pressure at point 1 and point 3 are equal, it means the best situation is happening to have the static pressure, and in further gain the pressure at point 2. Most likely, the rising along the yaw direction angles up to 12 to 20 degrees. Depending on the design, the errors are happening less than 1%. The detail of this design about the pitot, the static pitot tube, is having the beta as 21.5, which is the best situation happening for the calculating stagnation pressure from the static pressure. However, be careful about this. When you're reaching the high speed, as the compressibility is varying so much and the density is not constant, the shock waves as well as the supersonic situations might be happening, which is regarding the complex velocity equations, which is not attainable easily. So we have reached the end of this session. I'm really happy that you have accompanied me till this moment. Once again, I ask you to don't hesitate about asking your questions in the email or in the comment section of this video. Most importantly, please subscribe the whole channel in order to get the notification of upcoming instructional sessions. I bid you all farewell. See you in the next session.